There are stars so large, so vast in volume, that if placed where our sun stands, they would swallow Mercury, Venus, Earth, and keep going until the orbit of Saturn disappears beneath their skin. And yet, we cannot see them with the naked eye. They are hidden behind curtains of interstellar dust. Their light, powerful enough to blind the gods, is muted before it ever reaches us. They exist burning, dying, vast, and we only know them because we dared to ask the night deeper questions. What does it mean for something to be the largest? Is it a number, a volume, or a feeling, a confrontation with immensity that bends the edges of the mind? The largest stars in the known universe may not be the brightest or the closest. They may not even obey the laws we've written for the cosmos, but they exist. UY Scuti, Stephenson 218, two names whispered by astronomers, misunderstood by media, and haunted by paradox. Today, we uncover them. Please like and subscribe because this journey will change how you see our place in the universe. Prepare yourselves. We begin. To understand these giants, we must first step away from Earth, not just in distance, but in scale. Most of us think of the sun as large. It dominates our sky, fuels our seasons, and defines time itself. But compared to these red supergiants, our sun is a grain of sand. Let's reframe reality. If the sun were the size of a basketball, UY Scuti would be a house. If the sun were a car, Stephenson 218 would be a city block. These are not small differences. They are orders of magnitude, where understanding begins to dissolve. But even these metaphors fail, because space itself is the wrong metric. Size is not just spatial, it's temporal, it's energetic, it's gravitational. It is the echo of violence, the residue of time, the slow inflation of chaos. And when we look at UY Scuti and Stephenson 218, we are not merely studying stars, we are witnessing the limits of stellar identity, where matter begins to forget its own rules, where structure surrenders to expansion, where heat no longer guarantees pressure, and gravity becomes a whisper, barely holding it all together. Let's pause on that. How does something grow so large that it becomes nearly unstable? So cold that it teeters at the edge of collapse, and yet so luminous it bathes entire star fields in its fading breath? This is the contradiction we face. Stars like these shouldn't exist, at least, not for long, and yet they do, for now. But what makes them giants? UY Scuti, once hailed as the largest star known, is a red supergiant in the constellation Scutum, about 5,900 light-years away. Not visible to the human eye, but enormous. Its radius, once exaggerated to over 1,700 times that of the Sun, has since been revised with better distance measurements. Now, roughly 909 solar radii, still monstrous, swallowing the orbits of Jupiter and perhaps Saturn if placed where the Sun is, but no longer the crowned king. Why did this happen? Why did we think it was bigger before? Because in astronomy, distance is destiny. If you misjudge how far a star is, you misjudge everything about it: its brightness, its size, its energy. With the arrival of new data from Gaia, astronomers realized UY Scuti was closer than they thought. And that meant smaller, but not small, never small. Then came Stephenson 218, a name that sounds more like a spreadsheet than a celestial monument. But behind that name lies a mystery, a red hypergiant or supergiant, depending on who you ask, projected near a massive star cluster called Stephenson 2, roughly 18,000 to 20,000 light-years away. Here's the staggering claim: its radius, 2,150 times that of the Sunday, a photosphere that would reach beyond the orbit of Saturn, a volume 10 billion times that of our star, a fusion engine flickering at the edge of what's physically possible. But here's the catch: that number 2,150 is not certain. It's not carved in cosmic stone. It's an estimate based on assumptions. Assumptions about how far away it really island, assumptions about how cool it burns, assumptions about the dust that clouds our view. In other words, Stephenson 218 may be the biggest thing we've ever measured, or it may be a mirage built from shadows and guesses. This, then, is our stage. Two red giants. One, once thought to be the biggest, now scaled back to the size of a mere supergiant. The other, rising in its place, massive, mysterious, possibly mythic. What does it mean to chase the biggest? We humans are drawn to edges. The tallest mountain, the deepest trench, the farthest galaxy, the largest star, but the moment you reach it, it shifts. Not because the thing changed, but because you did. Your instruments improved, your models updated, your perception sharpened, and the universe, ever patient, whispers, "You are still learning." This is not a story about measurement. It's a story about our need to measure, to understand, to name the unknowable, to look up at the sky, draw a circle around a point of light, and say, "There, that one, that is the edge of everything." But the cosmos laughs, because for every UY Scuti we revise, for every Stephenson Toaden we elevate, there will always be another question waiting just beyond resolution, another shadow to chase, another contradiction to live with. So we begin this journey, not with certainty, but with curiosity, not with answers, but with awe. In the next chapters, we will dive deep into these stellar titans. We will unspool their light, unravel their winds, explore the burning ends of their lives, and compare them to the limits of theory itself. But remember this, the universe does not reward arrogance. It rewards wonder, and these stars hidden, enormous, dying, are not just cosmic facts. They are cosmic mirrors. Let's step into the light and the shadow of stars so large, they almost undo themselves. The unveiling of UY Scuti, the silent titan cloaked in dust. Some stars scream across the sky, others whisper from behind a veil. UY Scuti is the latter, a giant that has spent its life buried behind clouds of dust and gas, hidden not because of distance, but because of silence. It lives in the constellation Scutum, Latin for shield, a fitting name for a celestial body so well protected from our gaze. At nearly 5,900 light-years away, UY Scuti floats like a forgotten god, its light struggling to reach us, its heartbeat echoing faintly through the corridors of space. You've never seen it. You've likely never heard of it. And yet, if it replaced our sun, it would engulf the entire inner solar system. This is not a star that demands attention. It simply exists massive, slow, and collapsing under its own history. UY Scuti was once the largest known star. It wore the crown proudly for years, cited in documentaries, textbooks, even children's science books. But that crown was forged in assumption. Back then, we thought it lay around 9,500 light-years away, a distance that, when plugged into our models, gave it a radius of 1,700 solar radii. Our monster, but assumptions are fragile in astronomy. They crumble when touched by truth, and the truth came in the form of Gaia, a space observatory designed to map the stars of our galaxy with unprecedented precision. With Gaia's EDR3 data, the revised distance shrank. UY Scuti, it turns out, is much closer, just 1,800 parsecs, or about 5,900 light-years. That changed everything. Its brightness? Overestimated. Its size? Dramatically smaller. Its throne? Dethroned. Now, we estimate its radius at 909 times the size of the Sunday. Still enormous. Still enough to swallow Jupiter's orbit, but no longer the Titan we imagined. And yet, isn't that more fascinating? That a star can teach us humility, not through its size, but through the error in our own perception. The universe is not a monolith, it's a mirror, and in that mirror we saw a colossus, only to realize we were projecting scale onto uncertainty. We thought we understood, we thought we could measure, but the cosmos whispered, "Not yet, let's look deeper." UY Scuti is a red supergiant, not just red in color, but red in temperature, red in age, red in decline. It's the evolutionary phase that comes just before a massive star explodes into supernova. Its surface? Cooler than our sun by thousands of degrees. Its structure? A tenuous lattice of convective gas. So massive, yet so diffuse, you could fly a spacecraft through its upper layers without ever touching a solid surface. It pulses, not like a heart, but like a dying breath, expanding, contracting, a semi-regular variable star with a pulsation period of around 740 days. Each oscillation a reminder that this is not a static object. It's a star at war with itself. Surrounding it is a shroud of dust, not just cosmic debris, but the ashes of its own body, expelled in slow, steady hemorrhages of mass. UY Scuti is bleeding itself into the void. Its mass loss rate is staggering, about 5.8 times 10 to the power of -5 solar masses per year. That may seem small, until you realize that's 20,000 times the rate at which our sun loses mass. Every year, it sheds more of itself, and with each breath, its life shortens. This is the paradox of the giants. The bigger they are, the faster they fall. So what do we really know? Its luminosity is now believed to be around 124,000 times that of the Sunday, but earlier estimates using Gaia's older DR2 data put it even lower, closer to 86,000, 87,000 liters. Why the difference? Because even Gaia, for all its brilliance, struggles with stars like UY Scuti. The data is muddy. Astrometric noise clouds the parallax. The distance still carries uncertainty, and with it, so does every other measurement. This is a star made of ifs and almosts, a puzzle missing key pieces that may never be found, and yet we try. Because every correction, every reanalysis, brings us closer to understanding not just this star, but all stars. UY Scuti doesn't have a companion star, which makes determining its mass even harder. But based on its position in stellar evolution, models suggest it began with 7 to 10 solar masses. That may not sound like much, but by the time it bloated into its current state, it had burned through hydrogen, reshaped its core, and entered helium fusion. A transitional phase, the gate between life and collapse. It won't stay like this forever. Its destiny is written in fusion. Eventually, it will enter more chaotic phases, possibly becoming a yellow hypergiant, a luminous blue variable, or even a Wolf-Rayet star. And then, suddenly, violently, it will end. A core collapse supernova, the spectacular death of a massive star, scattering heavier elements across light years of space. Type IIb, type IN, maybe even IB or IC. The specifics are still debated, but the outcome is the same. One day, UY Scuti will de-infire, and it will give birth to something new. But until that day, it remains. A distant sun, hidden behind veils of dust, its light dimmed by the very material it created. You cannot see it with your eyes, but if your soul could sense gravity, you would feel UY Scuti like a presence pressing against the edge of thought. Not the largest, not the brightest, but maybe the most humbling. Because UY Scuti reminds us, even giants can disappear, even legends can be rewritten, even light can be misunderstood. So when you look at the sky and you don't see UY Scuti, remember, you're not looking too far. You're simply not seeing deep enough, where numbers bend and truth flickers like heat on the horizon. In the cosmos, nothing is more dangerous than precision built on a shaky foundation. We speak in absolutes, in kilometers, radi, solar masses, parsecs. We wield numbers like swords, pretending they slice through the unknown. But when it comes to the largest stars in the universe, sometimes the numbers lie, or worse, they seduce. Take a moment to imagine standing in the desert. The heat distorts the air. A shape emerges on the horizon, massive, shimmering. It looks like water, but as you walk toward it, it retreats. That is what measuring stars is like, especially the giants, especially when we ask them to be the largest. UY Scuti Stephenson 218. We wanted to know how big they are, but the moment we reached for certainty, the cosmos answered with a mirage. Distance, the first lie. Size in astronomy is a function of distance. You see how bright a star appears its apparent magnitude, and you plug in a distance to calculate its true luminosity, and from there, estimate its radius. But if the distance is wrong, the entire castle collapses. This is what happened to UY Scuti. We thought it was 2.9 kiloparsecs away. We were wrong. With better parallax from Gaia EDR3, we learned it was closer, 1,8 kiloparsecs. That one change, just a few thousand light years, reshaped its identity. Its radius dropped from a mythical 1,700 solar radii to a still massive, but far more reasonable 909 solar radii. Think about that. We had anointed a false king, crowned it the largest star, built documentaries around it, sculpted cosmic diagrams, all of it based on an illusion. Was it a mistake? Not quite. It was a phase, a necessary part of discovery, but it shows us something deeper. When you think you've reached the edge of understanding, you might just be walking into a mirage. Now shift your gaze to Stephenson 218. The numbers here are even more staggering: 2,150 solar radii. If real, it would make UY Scuti look like a sibling, not a rival. But again, how did we get that number? It's not measured directly. It's derived. From what? From assumptions. Assumptions about distance. We think it's around 5.5 to 6 kiloparsecs, about 18,000 to 20,000 light years. Assumptions about temperature. We assume it burns at a meager 3,200 Kelvin cooler than most red supergiants. Assumptions about extinction. We estimate how much dust lies between us and it, obscuring its true brightness. Each of these variables, riddled with uncertainty, stacked on top of each other like cards in a tower. One breeze, and the tower falls. Temperature, the second mirage. Temperature isn't just a detail, it's the lens through which we see a star. A hotter star with a given brightness must be smaller. A cooler star with the same brightness must be larger. So when we estimate a star's temperature, we are, in effect, estimating its size. Stephenson 218 is said to have a surface temperature of to 3,200 kelvins. That's low, so low in fact, that it raises red flags. Why? Because it approaches or exceeds the Hayashi limit, the theoretical line below which a star cannot remain in hydrostatic equilibrium. In simpler terms, if it's really that cold and that large, it shouldn't exist. And yet here it is on paper at least. But here's where things become stranger. If its temperature is off by even a few hundred degrees, say, it's actually 3,600 kelvins, then its estimated size plummet. Not by a little, by hundreds of solar radii. And that means Stephenson 218 may not be the largest star at all. It may be large, yes, but not impossible, not mythic, just enormous. And that changes the story. From anomaly to archetype, from rebel to relative, extinction, the final veil. But even with better distance and better temperature, there's one final curtain: dust. Interstellar extinction dims a star's light, and correcting for that dimming is both an art and a science. Too much correction, and you overestimate brightness, thus size. Too little, and you underestimate. But in the chaotic galactic plane where Stephenson 218 lives, extinction is a swirling mess of unknowns. Add in its possible but still uncertain membership in the Stephenson 2 cluster, and the assumptions stack even higher. Is it in the cluster, or just near it in projection? Does it share velocity? Metallicity? We don't know, and that not knowing infects everything else. So what are we really looking at? A star, or a story made of guesswork, dust, and data gaps? A lighthouse in the fog, or the fog itself? Yet here lies the beauty. The stars are not just things we study, they are tools to study ourselves. UY Scuti was not a lie. Stephenson 218 is not a delusion. They are reflections, mirrors that show how we learn, unlearn, and relearn. And isn't that cosmic in its own way? That the very act of measuring teaches us how fragile our measurements are? That every radius we cite is not a boundary, but a confession. This is as far as we've come. For now, somewhere out there, light is moving from a red giant, through the dust, through the centuries, toward us. It began its journey before your ancestors were born, before electricity, before names like UY Scuti or Stephenson 218 were etched into the scientific lexicon. And when it finally reaches our telescopes, we ask it, "How large are you?" And the light says, "It depends how clearly can you see me." Science is not about answers. It's about tension, the push and pull between what is and what might be. And when it comes to the universe's largest stars, we live in that tension. It's what makes the cosmos alive, not just in fusion and gravity, but in uncertainty. That is the miracle, that we are not measuring the stars, we are becoming them. The slow breathing of a star that knows it's running out of time. Even stars have heartbeats, not in the way our chests rise and fall, but in the expansion and contraction of matter, the rhythm of light, the pulsing of fusion, the slow, tragic music of collapse. UY Scuti pulses like this, a dying giant trying to hold itself together, vibrating with time and gravity, as if unsure which will claim it first. And if you listen closely, if you track its subtle flickers across years, you can almost hear it, a sigh, a breath, a warning. This star, buried behind dust in the constellation Scutum, is not still. It is not quiet. It is semi-regular, which means that every few hundred days, it beats, swelling and shrinking like lungs under pressure. Astronomers once modeled its pulsation period at around 740 days. But that number, like so many tied to UY Scuti, is haunted by its size. Because when we thought it was bigger, we thought its heartbeat was slower. Now that it's smaller, the models must shift. But no matter what numbers we assign, the essence remains. UY Scuti is a living instability. Why does a star pulse? Because its layers are at war. Gravity tries to crush the star inward. Radiation from fusion pushes outward. And when the balance tips, even slightly, the surface can balloon or fall inward. It's called stellar pulsation. And in UY Scuti, it reveals the fragile equilibrium of a body that has pushed itself to the edge of physics. These are not clean sine waves. They are chaotic, imperfect, like a dying animal gasping for air, but on a scale that spans light years. As the star pulses, it loses mass. Mass it will never recover. Mass that was once hydrogen, then helium, then heavier elements, nuclei forged in fusion, and then discarded into space. UY Scuti is wrapped in this ejected material, a halo of dust, gas, and ancient light that it made itself. Think of it like an atmosphere, or a ghost. The star's former self now drifting beyond its surface. This circumstellar envelope dims its light and hides it from our eyes. But infrared telescopes can see through the veil, and what they reveal is sobering. UY Scuti is not just dying, it is disintegrating. The mass loss rate is staggering, about 5.8 times 10 to the power of -5 solar masses per year. That's equivalent to 20,000 suns being vaporized across the galaxy every million years. And the thing is, UY Scuti isn't even that massive to begin with. Current models suggest a mass somewhere between 7 and 10 solar masses. That's small compared to some hypergiants. But this is what makes it beautiful. UY Scuti has inflated itself to cosmic absurdity, swollen into a massive cloud of hydrogen, helium, dust, and ash, just to survive a little longer. It's the last rebellion of a star, trying to resist its fate. We like to think of stars as eternal, but UY Scuti reminds us everything has a limit. Fusion doesn't last forever. Eventually, the core can no longer sustain the outward pressure needed to hold up the outer layers. The star begins to pulsate, to break, to fall inward. Inside, the core is likely fusing helium into carbon and oxygen. But it won't stop there. If the star survives long enough, it may enter a phase of shell burning, where different layers fuse different elements. Hydrogen in the outer shell, helium beneath that, then carbon, then neon, then oxygen, then silicon. Each new fuel source burns faster than the last. 8 steps shorter, more unstable, until, at the core, iron is born, and that's the end. Because iron doesn't give energy when fused, it takes it, and when the core becomes iron, it becomes doomed. The balance breaks, the collapse begins, and everything ends in light. But we're not there yet. Right now, UY Scuti is dancing at the edge. It breathes, it shudders, it pulses, and as it does, it leaves trails of itself across space. Astronomers have spotted extensive, dusty circumstellar material ejected by the star's violent convulsions. This dust could one day form planets, comets, asteroids, even life. UY Scuti is dying, but in its death, it is seeding the future. This, perhaps, is the greatest contradiction of all. Stars need to give birth, not to new stars, but to the elements that make stars possible. Carbon, oxygen, calcium, iron, everything in your body was once forged inside a dying star. And stars like UY Scuti, they are the forges, the factories, the parents, the martyrs. When it pulses, it's not just physics, it's poetry, a farewell letter written one atom at a time. We stare into our instruments and see a red, flickering blur. But if we could translate its light into sound, we would hear a song, not a melody, but a lament, a slow, low rhythm. I'm still here, I'm still burning, but not for long. And so the heartbeat continues, not in seconds, but in years, a rhythm that makes our own seem frantic and small. It expands, it cools, it collapses, it expands again, and in each motion, we witness a truth we rarely confront, that even the most massive things in the universe can be fragile, that even the brightest stars can be shadows of what they once were, that even the titans feel time. So what do we do with this knowledge? We remember it, we carry it, because the pulses of UY Scuti echo across space, but also across consciousness. They remind us that greatness is not eternal, that everything, no matter how vast, breathes its last eventually. And when that moment comes, it won't be silent. It will be beautiful, where the end begins and where endings become beginnings. Death is not the end for a star like UY Scuti. It is a transformation, a violent, luminous metamorphosis, so powerful it can be seen across galaxies, so final it rewrites everything it once was. And right now, UY Scuti is walking toward that destiny, but slowly, rhythmically, almost with grace. It is, in every sense of the word, dying beautifully. Let's be clear, UY Scuti is in its final phase of life. It has burned through its core hydrogen, entered helium fusion, and begun its descent into thermonuclear complexity. Layer upon layer of fusion shells now sit inside this star, like an onion of pressure and pain. Hydrogen fusing into helium, helium into carbon, and soon, if it hasn't already, carbon into neon, then oxygen, silicon. Each new layer fuses faster than the last. What once took millions of years now takes thousands, then hundreds, then days. This is the path of massive stars. They live fast, they burn hard, they die young. UY Scuti is not eternal. It was never meant to be. So what lies ahead? A metamorphosis, from red supergiant to something more unstable, more volatile, more mythic. One likely future is a transition to yellow hypergiant, a brief, blazing phase where the star heats up, loses mass at extreme rates, and changes color. These are the rarest stars in the galaxy, caught mid-transformation, wild, unpredictable, unstable. It might stay there for just a few thousand years, a cosmic blink before pushing further into oblivion. But the path doesn't end there. Another fate awaits, the Wolf-Rayet phase. These are the exposed cores of once massive stars, stripped of hydrogen, raging with helium and heavier elements. They spin, they scream, they die violently. For UY Scuti to become a Wolf-Rayet star, It must lose an enormous amount of mass. It is already trying. Its stellar winds are bleeding material into space at tens of thousands of Earths per year, and if it succeeds, if it survives the hypergiant phase, it may unveil its core, glowing blue and fierce, in a final blaze of fury. But even that would only be a prelude, because eventually, no matter which path it takes, UY Scuti will fall inward. The core grows heavy, iron forms, and when fusion can no longer continue, when there is nothing left to burn, gravity wins. The center collapses in milliseconds. The outer layers follow, and then a shock wave, a roar, a detonation, a supernova. The type is uncertain. It may be a type IIb, where most of the hydrogen has been lost. It may be a type IN, if surrounded by dense circumstellar material, or even type IB or IC, if it sheds its outer layers completely before the final act. But the classification doesn't matter. What matters is the power, the brilliance. For a few weeks, UY Scuti's explosion will outshine its entire galaxy. It will create a flash of light billions of times brighter than the Sunday. It will send shockwaves through the surrounding dust, igniting the gas it once exhaled. It will become a beacon of death, visible to telescopes across the Milky Way, and in its wake, chaos, and then creation. The iron core, now compressed beyond comprehension, may become a neutron star, a city-sized object so dense a teaspoon would weigh billions of tons. Or, if the mass is high enough, it may collapse further, deeper, beyond the event horizon. A black hole, a singularity, a place where time, space, and meaning bend. And UY Scuti will vanish, not with a whisper, but with a scream swallowed by gravity. But perhaps its legacy is not in how it ends, but in what it gives. Stars like UY Scuti are the furnaces of life. They forge the elements inside their cores: carbon, oxygen, nitrogen, calcium, iron. The calcium in your bones? It came from a star like this. The oxygen in your lungs? Forged in stellar fire. The iron in your blood? Born from the core collapse of a red supergiant? UY Scuti's death will not be the erasure of a thing. It will be the distribution of meaning, a recycling of atoms into new possibilities. Planets, comets, life, you, me, a child, a billion years from now on a world we have never seen. And so we ask, what is death really? If UY Scuti vanishes, but its body seeds a new generation of stars, is that annihilation, or is it rebirth? If it becomes a black hole, does that mean its story ends? Or does it just change format? A star becomes an explosion. An explosion becomes dust. Dust becomes a star again. This is the cycle. The fire and the fade, the burning and the breaking, and then the rebuilding. We often look at stars as symbols of permanent, eternal flame. We say, guiding light. But UY Scuti reminds us, the stars are not eternal. They are fleeting, just like us. The difference is only scale. And perhaps that's the most human truth buried in this cosmic tale, that even when we are enormous, even when we shine, even when we pulse with light and heat and energy, there will come a time when we must let go of our mass, our pride, our boundaries, our illusion, and in that letting go, we create space for something new, something better, something unknown. UY Scuti is not the biggest, not anymore, but perhaps it is the clearest mirror, a reminder that greatness is not static, that to grow, sometimes you must dissolve, that even giants must fall, so the galaxy can rise. Some giants burn like fire, others drift like ghosts. What if the largest thing you've ever imagined is something you'll never truly see? Not because it's invisible, but because reality itself refuses to resolve it. This is the mystery of Stephenson 218. A star so vast, so distant, so cold, that its existence feels like a rumor whispered through dust. It doesn't blaze, it looms, a fading breath from the edge of perception. If UY Scuti is a red lantern in a smoky room, then Stephenson 218 is a forgotten cathedral, buried in fog, its spires scraping at the limits of theoretical physics. It doesn't announce itself. It waits, patient, monstrous, maybe mythical, and yet our models say it's real. They tell us this star's radius might be over 2,150 times that of the Sunday. If placed at the center of our solar system, its surface would stretch well beyond Saturn, not just dwarfing Earth, not just swallowing Jupiter, but consuming the realm of giants. That's not just large, that's category breaking. Its name lacks poetry. Stephenson 218, also called Stu18 or Stephenson 2 DFK1. It sounds more like a lab sample than a myth, but don't let the name fool you. This star, if the numbers hold, would be the largest stellar object humanity has ever measured. Not just larger than UY Scuti, larger than Betelgeuse, larger than VY Canis Majoris, larger than the limits of our confidence. And that's the key word here, confidence, because unlike UY Scuti, which has been revised downward by clearer data, Stephenson 218 sits in a realm of uncertainty so thick, it might as well be dark matter. Let's start with where it lives. The star is projected near the massive open cluster, known as Stephenson 2, about 18,000 to 20,000 light-years away in the direction of the Scutum constellation. And that's already a problem. We don't know for certain if it's in the cluster or just appears near it by chance. Its radial velocity doesn't quite match. Its position is close, but that doesn't prove membership. Without that confirmation, we can't be sure of its distance. And without knowing distance, every estimate of size, brightness, mass is a house of cards. But let's indulge the possibility. Let's assume for a moment that the distance is real, that the star is 5.5 to 6 kiloparsecs away, that its light has traveled nearly 20,000 years just to touch our detectors. What does that light say? It says, the star is cooler than it should be. Much cooler. Estimates put its surface temperature around 3,200 Kelvin, a number that challenges theoretical limits. Because below a certain temperature, a star can't support itself. It becomes unstable. It collapses or flares into something else. This temperature places Stephenson 218 at or beyond the Hayashi limit, the theoretical boundary for how cold and large a stable star can be. It's not just rare, it's borderline impossible. So again, is this a star or an observational hallucination? Let's talk size. That 2,150 solar radii figure is built on a fragile equation. The star's apparent brightness, its assumed distance, its extremely low temperature, its heavy extinction due to dust. From those, scientists derive luminosity and then back-calculate the radius using the Stefan Boltzmann law. And that's where the number comes from. It's not a measurement. It's a model dependent on multiple uncertain inputs, which means if any one of those inputs is wrong, the entire estimate could fall apart. The star might be 1,500 solar radii, or 1,000, still giant, still majestic, but no longer the record holder. And yet, what if it is right? What if, even through the noise, the distance, the dust, the extinction, we are staring at something that should not exist? What then? Its luminosity is equally staggering. Estimates again, built on assumed distance, and extinction place it between 440,000 and 630,000 times the luminosity of the Sunday. That's enough energy to power entire regions of space. It lights up its local cluster like a red lighthouse in a sea of black. And yet, even with that luminosity, its temperature stays low, its radius stays enormous, its spectral type stays late around M5 to M6. This is not the signature of a healthy star. This is a star bloated beyond balance. There is something eerie about Stephenson 218. UY Scuti feels warm, emotional, even tragic. But this feels alien, a quiet god asleep in the dark. Its surface cool, yet its power immense. It doesn't flash. It waits. It doesn't scream. It hums deep, slow, and unreadable. Some have suggested it might be a hypergiant, a classification reserved for stars that are not only massive, but unstable, variable, shedding mass at incredible rates. And indeed, Stephenson 218 shows signs, strong infrared excess, maser emissions from molecules like SiO and H2O, heavy, dusty outflows, spectral broadening. It's not just big, it's actively breaking itself apart. Its outer layers aren't holding steady. They're leaking, falling, melting into space, like a frozen mountain, slowly becoming a storm. But here's the strangest part. Despite its theoretical mass loss, its luminosity, its massive size, Stephenson 218 remains elusive. There is no companion star to help determine its mass. There is no confirmed cluster membership to lock in its distance. There is no parallax from Gaia. The star is too far, too dusty, too faint for precision astrometry. It is the perfect cosmic ghost, visible but unverifiable, measured but not known. So what are we to make of it? A data artifact? A record breaker? A challenge to the limits of stellar theory? Maybe all three. Maybe that's the point. Because sometimes the universe leaves loose ends on purpose, not as errors, but as invitations. Stephenson 218 is not just a star, it's a question wrapped in dust, wrapped in time, wrapped in our desire to believe that something larger than possible can still be real, where certainty dissolves and the universe stares back. At the outer edge of knowledge, the universe doesn't offer answers, it offers mirrors. And when we peer into Stephenson 218, we don't just see a star, we see ourselves, straining to make sense of something that might be unknowable. A star so large it defies the limits of physics, so distant it mocks our precision, so veiled in dust and error margins that even its existence as the largest is a question, not a conclusion. And in that tension, in that liminal space between what might be and what can be known, we find ourselves at the edge of understanding. There's a myth in science that we're always moving forward, that uncertainty is temporary, that every question is a door, just waiting for the right key. But Stephenson 218 is not a door. It's a fog. You step into it with instruments and models and equations, and still, you're surrounded by grey. Where is it? What is it? How big? How hot? How real? Every answer spawns another doubt. Every fact frays into speculation. And yet this is not failure. This is the front line of discovery. Let's return to the basics. The foundation of any star's profile, its mass, size, brightness, depends on one pivotal measurement, distance. And Stephenson 218 lives in a region of the galaxy where that is infamously hard to determine. The Scutum star-forming complex is a crowded neighborhood, thick with dust, brimming with stars, and riddled with extinction that distorts what we see. Gaia, our greatest stellar cartographer, can't lock onto it. Its parallax data? Too noisy, too uncertain. Its distance remains assumed, not confirmed based on association with the nearby cluster Stephenson 2. But here's the problem. Stephenson 218 might not even belong to that cluster. Its radial velocity doesn't match. Its movement diverge. Its chemical signature may differ. It might just be passing by, aligned by chance. And if that's true, if it's not 20,000 light years away, but perhaps closer or farther, then everything collapses. Its radius, its luminosity, its record, gone. And yet, the possibility lingers that we are seeing something genuinely colossal, a star whose reality bends our models, a supergiant or hypergiant that sits right on the cliff where physics threatens to break down. Why? Because the numbers, for all their instability, continue to suggest it's just barely possible. A star with a radius over 2,000 times the Sun, a temperature near 3,200 kelvins, a luminosity greater than 500,000 suns, an envelope shedding mass into the cosmos, a star at the very edge of what the Hayashi limit allows. In other words, a theoretical tightrope walker. One misstep, and the laws say it shouldn't be here, and yet they're at island. There is a beauty in this contradiction, because science is often mistaken for certainty, a list of facts, a book of rules. But the truth? Science is the art of doubt. It is the patient practice of asking better and better questions. And Stephenson 218 forces us to ask, what if our limits are too small? What if the Hayashi line isn't a hard wall, but a suggestion? What if our models, based on nearby stars and solar logic, simply don't apply here? What if we're trying to measure a god with a ruler made for ants? It's tempting to retreat, to wait for more data, to declare, we don't know yet, so we'll say nothing. But that's not how wonder works. Wonder lives at the edge. It thrives in ambiguity. It feeds on paradox. Stephenson 218 doesn't just stretch our instruments. It stretches our imagination. It asks, how big is too big? How cool is too cool? How much uncertainty can we tolerate before a thing becomes myth? And maybe, how much mystery are we willing to live with? Because this is the uncomfortable truth. You can know everything about a star's light spectrum, its emission lines, its infrared excess, its maser activity, and still not know the star. You can measure the breadth of a giant and not know the size of its chest. You can name a thing and still be lost in its presence. That is the edge of understanding. It's not a line we cross. It's a cliff we stare into. And sometimes the stars stare back. But rather than pull back, we can lean forward. We can learn to live in this space. Not knowing, but wondering. Not measuring, but marveling. This is not ignorance. It is reverence for a universe that hides its greatest wonders behind veils of ambiguity. For a cosmos that asks us to look not just with instruments, but with humility. Stephenson 218 may not be the largest. It may not even be what we think it island. But the questions it raises are larger than the star itself. What defines a limit? When does a boundary become a belief? How do we distinguish reality from our longing for something beyond it? So here we are, not at the end of knowledge, but at its edge, looking out, not afraid, but honored, because this, more than any discovery, is the reason we look up, not to conquer the stars, but to be humbled by them. When a star tiptoes past the edge of theory, what do we trust, the equations or the evidence? There are boundaries in the universe that don't exist on maps. Not borders, not walls, but invisible limits etched in mathematics. Equations whispered into being by theory. Lines drawn not in sand, but in the behavior of stars. One of these limits is called the Hayashi line, and Stephenson 218 may have quietly stepped across it. Not with a bang, not with a scream, but with the soft rustle of physics, unraveling at the seams. The Hayashi line is not something you'll see through a telescope. It's not painted on the sky. It lives in the Hertzsprung-Russell diagram, a map of stars where luminosity dances against temperature. The diagram shows us the life cycles of suns, where they are born, how they evolve, where they die. But the Hayashi line, that's where stars cannot exist, at least not stable ones. It marks the lowest temperature at which a star of a given mass can still maintain hydrostatic equilibrium, a balance between gravity pulling in and pressure pushing out. Cross that line, and a star becomes unstable, collapsing, or something else entirely. For red supergiant stars near the end of their lives, bloated and burning helium, this limit sits around 3,500 Kelvin. Dip below that, and the models fall apart. No pressure, no balance, no star, and yet, Stephenson 218 appears to sit at around 3,200 Kelvin, a ghost with blood too cold, a giant standing where giants shouldn't stand. How can this be? Either the temperature is wrong, or the rules are incomplete. Let's take the first option. Perhaps we've misunderstood the spectrum. Perhaps the heavy extinction in Stephenson 218's region is warping its true color. Perhaps the veils of dust, gas, and interstellar noise have tricked our instruments into thinking it's colder than at island. A few hundred Kelvin, just 300 or 400 degrees, could push it back across the Hayashi line. It would still be massive, still luminous, Still fascinating, but it would be safe. Inside the known, inside the rules, that would be comforting. But maybe that comfort is false. What if the temperature is real? What if Stephenson 218 is as cold as it seems, and yet somehow still holding together? That would mean the Hayashi line isn't a wall. It's a threshold, a guideline we mistook for law. It would mean our models, elegant as they are, have missed something essential. Something about extreme mass loss. Something about envelope inflation. Something about how stars can live briefly on the other side of stability. It wouldn't be the first time. The universe is littered with objects that shouldn't exist. Pulsars spinning faster than theory allows. Exoplanets skimming their stars too close to survive. Black holes larger than models predicted. Galaxies forming too early in cosmic history. Stephenson 218 may be just another anomaly, or it may be a lesson that the universe is not beholden to our diagrams. There's a term astrophysicists use when a star behaves badly: non-standard. Stephenson 218 is deeply non-standard. Its massive size, low temperature, and luminous output challenge our assumptions about red supergiants, stellar opacity, and convective boundaries, and yet, there it is fitting into none of the boxes we made. We try to force it back into the diagram, adjust the dust, tweak the model, shift the spectral classification, but the star resists. It refuses to shrink, refuses to warm up, refuses to be easy. It just exists, like a celestial protest, a reminder that the cosmos will always be bigger than our understanding. And perhaps that's the deeper truth. The Hayashi line was never a wall in the universe. It was a line in our minds, a frontier drawn by what we believed was possible. And when a star like Stephenson 218 steps over that line, it doesn't break physics, it evolves it. We don't abandon the models, we refine them, because real science isn't about defending the diagram, it's about changing the diagram when reality demands it. If Stephenson 218 is real, if it is that cold, that large, that luminous, then we are witnessing something transitional, a phase so brief, so volatile, so strange, that only a handful of stars will ever experience it. It might be inflating wildly as it sheds mass. It might be in the moments before collapse. It might be shifting from red supergiant to yellow hypergiant, or to Wolf Rayet, or to nothing at all. It may not be breaking the rules. It may just be writing new ones. And if that's true, then Stephenson 218 becomes more than just an object. It becomes a signpost, pointing to the outer edges of theory, to the places where physics, chaos, and cosmic evolution blur. It is the flame at the edge of the map, the whisper in the quiet library of stellar evolution that says, there are still pages left to write. The Hayashi line gave us confidence. It gave us boundaries. It helped us understand where stars belong. But perhaps now it is time to redraw those lines, to accept that even in science, especially in science, truth is a moving target. And sometimes the stars lead us where our equations dare not follow. So let Stephenson 218 stand. Let it burn cold. Let it tower above Saturn's orbit. Let it shed its skin and confuse our models and make us uncomfortable. Because discomfort is where discovery begins. And when a star crosses the Hayashi line, it doesn't just stretch theory, it expands us. When stars die, they do not go quietly. They tear themselves apart molecule by molecule, whispering their last breath into the cosmos. A star is not solid. It has no skin, no edge, no boundary you can touch and say, here it ends. It is held together by a conversation, gravity pulling in, radiation pushing out, silence balanced against explosion. But when that balance falters, when gravity grows tired and radiation grows wild, the edges begin to blur, and a star like Stephenson 218 begins to leak. This is where we find ourselves now, at the edge of stability, at the point where the body of the star becomes porous, and the universe begins to take it back. Stephenson 218 isn't just massive. It isn't just cold. It is falling apart. Its outer layers are being stripped, atom by atom, by stellar winds so vast, they make hurricanes look like sighs. These aren't breezes. They are eruptions, slow, unrelenting outflows of mass, carving rivers of dust into the night. Let's be precise. The mass loss rate for Stephenson 218 has been estimated at around 1.35 times 10 to the power of -5 solar masses per year. That's the mass of 5 Earths, cast off every 12 months, gone, vaporized, dissolved into the void. This is not cosmetic. This is not gentle. This is disintegration, and it doesn't stop at matter. Stephenson 218 is a MESA machine, emitting intense, focused microwave radiation from molecules in its circumstellar envelope. These mesas, especially SiO, silicon monoxide, and H2O, water vapor, are not just scientific curiosities. They are signposts of chaos. They form in regions of extreme heat, pressure, and motion, where molecules are being slammed, excited, and hurled outward by the energy of a star in collapse. Imagine watching a bonfire, and instead of just light, it begins emitting laser-like beams from within its smoke. That is what mesas are, not metaphor, reality. Stephenson 218 is so unstable, even its atoms have begun to scream. And what do these mesas tell us? They tell us the star has already shed enormous portions of itself, that its outer shell is no longer a boundary. It is a storm, a fog of gas and dust, stretching light years wide, glowing faintly in the infrared, echoing with microwave static, drifting through time. This fog is rich in secrets. What was once part of the star's atmosphere, elements fused in its core, traces of heavier atoms born in its nuclear furnace, all of it now adrift, waiting to cool, waiting to collapse, waiting to become something else. But here's the twist. This destruction is not tragic. It is necessary, because this is how the galaxy renews itself. Massive stars, like Stephenson 218, are the great recyclers. They fuse the simple into the complex, and then they donate it back. They exhale carbon. They shed oxygen. They bleed calcium, silicon, iron, and these elements become planets, atmospheres, oceans, life. Everything we are was once a part of this process. We are made from stellar waste, from the bones of stars that died screaming into the void. So when Stephenson 218 throws off its skin, it is not dying in vain. It is fertilizing the future. Its winds, violent, choking, brilliant, will one day cool and coalesce, forming new stars, new systems, perhaps even worlds like ours. This is not disintegration. It is donation. It is generosity on a cosmic scale. And what remains at the center? A shrinking, trembling core, dense with fusion, straining to hold together as the layers above it fly apart. This is a countdown, not to seconds, to centuries, to decades, maybe even years. But the fuse is lit, and once enough mass is lost, once the balance tips just slightly more, the core will collapse. Perhaps it will become a Wolf-Rayet star, a stripped-down, furious skeleton of helium and heavier elements. Perhaps it will skip that step entirely and go straight into supernova. No one knows, because no one has caught a star exactly like this in exactly this moment. Stephenson 218 is too far to observe in detail, too shrouded, too unique. But its symptoms are clear. This is terminal behavior, a star unmaking itself in slow motion, one solar mass at a time. And the visuals? If we could stand near it somehow shielded from death, we would see a swollen, blood-red orb, a dim glow, not piercing, but drowning, tendrils of gas swirling into the abyss, dust lanes sculpted by magnetic chaos, Mars flares popping like lightning in a thundercloud. It wouldn't look like a star. It would look like a planet in flames, or a sun melting into its own sky, and we would understand, without words, this is not the peak of glory. This is the prelude to surrender. So what does it mean to watch a star unravel? It means we are watching the future of everything, because what happens to Stephenson 218 will happen to countless stars. And what happens to them will happen to us, not in fire, but in transformation. Our atoms are borrowed, our lives are temporary, but our matter, our carbon, our calcium, our iron, will return back into the stream, back into the stars. Stephenson 218 is disintegrating, not out of weakness, but out of purpose, and the winds it casts into the void are not cries of defeat. They are prologues to rebirth. In a sea of giants, one star refuses to belong. Or does it? Not all mysteries lie in the stars themselves. Some are hidden in the company they keep, in the patterns, in the movements, in the dance of stars born from the same molecular cloud, sibling suns cast into the spiral arms of the galaxy. Stephenson 218 sits in the line of sight of one of the Milky Way's most massive open clusters, Stephenson 5, and for years, scientists thought that's where it belonged, that this enormous, possibly record-breaking red supergiant was just one of many children from this stellar nursery. But as with everything about Stephenson 218, the closer we look, the less certain we become. Stephenson 2, the cluster, is a jewel box of dying giants, a graveyard in slow motion. It contains dozens of red supergiants, a population so unusually rich, it stands out even in a galaxy filled with stars. Located roughly 18,000 to 20,000 light-years away, Stephenson 2 is buried in dust, but not invisible. Infrared telescopes pierce the veil, revealing a swarm of massive stars, many near the ends of their lives, cooling, swelling, preparing for collapse. This is a cosmic retirement home for titans. And on the edge of this glowing assembly, Stephenson 218. But here's the question that changes everything. Is it truly one of them? To answer that, astronomers turn to motion, to radial velocity, the speed at which a star moves toward or away from us. If Stephenson 218 shares the cluster's velocity, that would strongly suggest membership, a shared birthplace, a shared history, a common origin written in gravitational code. But here's the problem. Stephenson 218's radial velocity doesn't quite match. It's close, temptingly close, but not exact. And in a system as massive and crowded as this, close is not enough. This discrepancy ripples outward. If Stephenson 218 isn't part of the cluster, then all distance assumptions crumble. We estimate its distance based on cluster membership. We estimate its luminosity and radius based on that distance. Remove the cluster, and you remove the scale. It might not be 2,150 times the radius of the Sunday. It might be smaller, merely enormous, not impossible. Suddenly, the star collapses back into model, into comfort, into something we can understand. But there's another possibility, a darker one, a more mysterious one. What if Stephenson 218 is part of the cluster, but is simply different? Different motion, different history, a rogue within a family of giants. That wouldn't just make it the largest, that would make it the strangest. A star born from the same cloud as the others, but evolving along a different trajectory, perhaps more massive at birth, perhaps affected by a now vanished companion, perhaps experiencing extreme mass loss that altered its motion. Clusters evolve, just like stars. They expand, stars drift apart, tidal forces stretch them, encounters with other masses twist their trajectories. What if Stephenson 218 is simply on its way out? A member of Stephenson 2, but caught in the act of departure? Then its discordant motion isn't disproof. It's a snapshot in a dynamic story. The truth may lie in the chemistry. Stars born from the same cluster often share metallicity, the proportion of elements heavier than hydrogen and helium. Compare Stephenson 218's chemical fingerprint to that of confirmed cluster members, and you may find a match or an intruder. But even here, the data is murky. Dust complicates spectroscopy, faintness obscures detail, and at nearly 20,000 light-years, certainty is a luxury. All we're left with are probabilities, guesses, partial truths, and a single giant star that hovers at the boundary between association and isolation. But perhaps this is the deeper metaphor. Some of the most exceptional things in the universe do not belong easily. They skirt the edges of categories. They defy grouping. They refuse to play by the rules of proximity. Stephenson 218 is like that. Too far to confirm, too different to dismiss. A star caught between belonging and being alone. And if it is not a member of Stephenson 2, if it's just passing by, a foreground or background object, what then? Then its distance becomes unknown. Its brightness becomes a guess. Its size becomes an illusion built on assumption. And perhaps that's the truest thing we can say about it. That Stephenson 218 is a mirror, reflecting the danger of needing stars to fit into structures. Clusters give us comfort. They anchor our data. They offer context. But they also limit us. Because not everything large needs a home. Not everything massive must be understood by who it stands beside. Some things must be understood on their own terms. And that might be Stephenson 218's greatest defiance. Not its size, not its temperature, but its solitude. Aroga titan, carving its path, bleeding into space, uncategorized. It's ironic, isn't it, that in a region filled with dying giants, the most mysterious one is the least confirmed. It is there, but always somewhat elsewhere. Part of the story, but also the footnote. A shadow at the edge of the bonfire. And maybe that's the message the universe keeps whispering. That what matters most doesn't always fit the structure. That the outliers, the misunderstood, the drifting, the discordant, are sometimes the ones who teach us the most. Even in the cosmos, even among stars. What happens when something in the universe becomes too big to make sense? Every structure has a limit. A skyscraper too tall will collapse under its own weight. A bridge too wide will buckle with strain. Even mountains, given time, erode and fall. And stars? They have limits too. Not just to their brightness, or their mass, or their lifespan, but to their size. Somewhere beyond the swelling atmospheres of red giants, beyond the dusty shells of hypergiants, beyond the luminous fury of blue stars, there is a wall, a boundary where the physics says, you can't go any further. And yet, Stephenson 218 might have gone there, or beyond. According to modern astrophysics, the upper limit for a red supergiant's radius in the Milky Way is around 1,500 solar radii. That's not a guess. It's derived from the intricate interplay of stellar mass, luminosity limits, envelope opacity, convective stability, and the immutable force of gravity. You can be bigger, yes, but only if you're also cooler, or lighter, or collapsing. Push all the variables too far in the same direction, and the star becomes impossible, a structure too bloated to hold itself together. Stephenson 218 is often cited at 2,150 solar radii. That's 43% beyond the accepted theoretical maximum. It's not a small overshoot. It's not a rounding error. It's a direct confrontation with the laws of stellar evolution, and it begs a question that hangs over every model, every paper, every telescope image. Can this be real? To answer that, we have to understand why the limit exists. At the heart of every star is a wall between gravity pulling inward and pressure from radiation and fusion pushing outward. But as a star expands, its outer layers become more diffuse, more delicate, less bound. At a certain point, the outer atmosphere is so loose, so far from the gravitational grip of the core, that a whisper of radiation can blow it away. This is what defines the limit. Go past it, and the star can no longer hold itself together. It bleeds, it sheds, it dissolves like fog in sunlight. That's why most red supergiants top out around 1,000 to 1,400 solar radii. So what does it mean if Stephenson 218 really is 2,150? It means something is wrong. Wrong with our models, wrong with our data, wrong with the assumptions we make about opacity, mass loss, or temperature. Perhaps it means that exceptions exist. Rare, violent, brief, but real. A A star may spend only thousands of years in such a state, a cosmic blink, but in that time, it may balloon beyond the limits we drew for it. Not because the star is breaking the rules, but because we haven't written all of them yet. Let's reframe. Theoretical limits are not prisons. They are boundaries of current understanding. They are the edges of the map where we wrote, "Here there be dragons." Stephenson 218 may be one of those dragons, a monster in the margins, a data point too big to ignore, too strange to trust, too rare to dismiss. There's precedent for this. In the 20th century, astronomers thought stars couldn't be more massive than 60 solar masses. Then we found stars with 100, then 150, and even beyond 200 solar masses in the Large Magellanic Cloud. We thought we knew. We were wrong, and the universe was patient in correcting us. Stephenson 218 may be another correction, a reminder that our theories are not the ceiling, they are the floor we build from. But even if its radius is exaggerated, even if future data revises it downward to 1,800 or 1,600, the fact that we had to consider 2,150 is significant, because it means our models are sensitive, precarious, balanced on assumptions of distance, temperature, dust, and brightness. It means we're walking a tightrope across the cosmos, and stars like this test how well we walk it. Still, this isn't just a scientific tension, it's an emotional one. There is something deeply human about needing the biggest star, the brightest, the farthest, the most extreme. We crave limits so we can find what breaks them. We define maximums so we can celebrate the exceptions. And Stephenson 218 stands, for now, as that exception, a possible record, a possible outlier, a possible myth that turned out to be true. But what if it's not? What if it's just a trick of dust and math? What if it's smaller? Normal? Would that diminish the wonder? Number? Because the true story isn't the number. It's the journey, the challenge, the willingness to question our most sacred equations, the courage to stand at the edge of what we think is possible and ask, what if the universe is even stranger than this? And that's the wall, not 500 solar radi, but the wall in our minds, the part of us that demands certainty, that fears contradiction, that resists the idea that sometimes things just don't fit. Stephenson 218 isn't just a star, it's a confrontation with size, with theory, with ourselves, and whether it is 2,150 solar radii or not, it has already broken the most important limit of all, our willingness to be surprised. Between signal and silence, numbers become stories, and stories become legend. It starts with light, a faint pulse from the darkness, crossing thousands of years of emptiness, arriving as little more than a whisper. That light hits a mirror, a sensor, a mind, and from it, we build a star. We measure its brightness, estimate its distance, infer its size. We run simulations, cross-check catalogs, adjust for extinction, and from this fragile scaffold, from this web of approximations, we name the impossible, the largest star ever discovered. But what if we're wrong? What if the data that gave us Stephenson 218 as a cosmic giant is not a truth, but a story we told ourselves to make sense of something unclear? Not a lie, but not the whole truth either. Because science, despite all its rigor, does not always begin with certainty. It begins with inference, with signal, with interpretation. And sometimes, what we interpret becomes so vivid, so emotionally satisfying, that we forget it was built on assumptions. This is how myth begins, not in error, but in desire. The desire to see something larger than life, to discover a new extreme, to be the generation that finds the next superlative, the farthest, the fastest, the brightest, the largest. Stephenson 218 arrived in this vacuum, an unusually cool, unusually luminous red star near a massive cluster, just distant enough, just uncertain enough to allow for grand possibilities, and we built a legend from it. 250 solar radi, a volume 10 billion times the Sun day, a photosphere that would engulf Saturn. It became a headline, a record, a new chapter in the cosmic Guinness Book. But beneath that headline, uncertainty. Let's retrace the myth-making. A rough distance of 5.5 to 6 kiloparsecs, based on nearby cluster proximity. A low temperature, estimated at 3,200 kelvins, dangerously close to or beyond theoretical stability limits. A faint, dust-obscured glow interpreted through reddening correction models. A spectral type de Riehl under difficult conditions. A radius calculated not measured by applying Stefan Boltzmann's law to inferred luminosity and temperature. Each of these inputs is a layer of interpretation. Each carries margin of error. Each rests on the one before it. And when you stack assumptions like that, you don't get a star, you get a mirage. But here's the haunting part. We knew that. Every astrophysicist who published those numbers included caveats, assuming a distance of x. If the temperature is indeed y, based on current extinction models, the uncertainty was written into the papers, into the footnotes, into the methods sections, but by the time it reached the headlines, the caveats were gone, and in their place, a myth, because myths aren't false, they're functional, they help us organize the unknown, they help us feel like we've grasped something too big to hold, and in astronomy, myths are born when data is uncertain, but the desire to know is overwhelming. We want the largest star, we want to stand beneath it, to say we've found the new frontier, and so we simplify, we exaggerate, we romanticize, not out of malice, but out of a deep human yearning. Stephenson 218 is the perfect myth candidate. Far enough away to be unreachable, cold enough to be mysterious, massive enough to defy models, ambiguous enough to resist clarity. It exists in that twilight between fact and awe, between numbers and narrative. But science, at its best, is not afraid of myth. It examines it, dissects it, understands why it arises, and gently, respectfully, corrects the record. So maybe Stephenson 218 is not 2,150 solar radii. Maybe it's 1,600 or 1,200 or 950, still massive, still wondrous, just not a boundary breaker. And that's okay, because the real lesson isn't in the number. It's in how we handle the uncertainty. Do we cling to the myth because it feels good? Or do we walk into the fog again, armed with better tools, ready to ask again, more clearly? There's a deeper reflection here. Science and myth are not opposites. They are partners. Science begins in wonder, and myth is what we create when wonder outpaces understanding. Stephenson 218 is a product of both. A star we can barely see, barely measure, barely place in context, but one that inspires. That draws curiosity, that raises questions, that pulls us toward the edge of knowledge and asks, what if the world is still stranger than we know? So let us honor the myth, not by believing it blindly, but by letting it lead us deeper. Let the data be messy. Let the errors be loud. Let the numbers shift as the models grow stronger, but never let go of the emotion behind it. The need to know, to reach, to imagine, to build a world from whispers of starlight. Because in that act, in that beautiful, imperfect act, we are doing the most human thing of all, turning uncertainty into meaning. When the cosmos gives us two monsters, the comparison isn't about victory, it's about understanding. Every legend needs a rival, every myth a mirror, and in the story of the universe's largest stars, two names rise above the rest. UY Scuti and Stephenson 218, both colossal, both ancient, both unraveling, yet so different, they seem born from different laws, as if gravity shaped them with opposing philosophies. This is not a battle, it's a revelation, because to compare these stars is to compare two paths to oblivion, two answers to the same cosmic question. How big can something be before it ceases to make sense? Let's begin with the most seductive quality, size. UY Scuti's revised radius, after better distance estimates via Gaia, lands at around 909 solar radii. Still vast enough to swallow Jupiter's orbit. Still one of the largest confirmed red supergiants. But Stephenson 218, it is often cited at 2,150 solar radii, a radius that stretches beyond Saturn, possibly Uranus. If both stars were placed at the center of our solar system, UY Scuti would erase Earth, Mars, and possibly Jupiter. Stephenson 218 would make even Saturn disappear into flame. But that's under one crucial word, if, because while UY Scuti's size is grounded in improved parallax and modeling, Stephenson 218's numbers lean heavily on assumptions of distance, temperature, extinction. One star is measured, the other is interpreted, and yet we must hold them side by side. Now, distance. UY Scuti lives about 5,900 light-years away, close enough for Gaia to offer useful data. Stephenson 218 is believed to be 3 to 4 times farther, at around 18,000 to 20,000 light-years, projected near the dense Stephenson 2 cluster. But here's the twist. That cluster membership isn't confirmed. If Stephenson 218 is closer or farther than we think, then its size, brightness, and identity change entirely. UY Scuti is known. Stephenson 218 is theoretical. And then there's temperature. UY Scuti is cool for a star, but not impossibly so, hovering around 3,365-3,700 kelvins, depending on modeling. Stephenson 218 is estimated at to 3,200 kelvins, possibly dipping below the Hayashi limit, the red line of stellar stability. If true, it shouldn't even exist in its current form. It pushes against the boundary of what red supergiants can be, a candle too large for its own flame. UY Scuti pulses within reason. Stephenson 218 breathes against reason. What about luminosity? UY Scuti's light output, again, revised downward with better distance, is about 124,000 times the Sun's. Stephenson 218, depending on distance, it's believed to shine with 440,000 to 630,000 solar luminosities. That would make it several times brighter, even though its surface is cooler. This contradiction only works if the star is truly enormous, spreading that dim red light across a surface that spans billions of kilometers. In other words, Stephenson 218 may not burn hotter, but it burns more. Then there is variability. UY Scuti is a semiregular variable, pulsing every to 740 days, expanding and contracting like a living organism. Its fluctuations are subtle, predictable, rhythmic. Stephenson 218 is not a standard variable, but it is not still. Its outflows, maser activity, and dust shedding suggest a turbulence that is harder to track, a chaos too vast for our timelines to decode. One beats like a slow heart, the other dissolves like weather. Now to the skin, mass loss. UY Scuti ejects material at a rate of 5.8 times 10 to the power of -5 solar masses per year, a furious stellar wind, driven by pulsation and radiation pressure. Stephenson 218, slightly less aggressive, clocks in at 1.35 times 10 to the power of -5, but its signature is different. Masers, dense dust, and extreme infrared excess. It is not screaming, it is bleeding. Each casts pieces of themselves into the dark, fueling the interstellar medium, making dust that will one day become worlds. And now, the final tension, certainty. UY Scuti has been revised. It was once thought to be the largest, but new data humbled it. And in that humility, it became more real. Stephenson 218, by contrast, remains perched atop uncertainty, more myth than measurement, more probability than portrait. One is anchored, the other adrift, but both matter, because in comparing them, we learn what science actually is. Not just a catalogue of facts, but a method of navigating between what is known, what is assumed, and what we hope might still be discovered. If UY Scuti teaches us about revision, Stephenson 218 teaches us about possibility. One reminds us that the truth can be smaller than we imagined, but no less magnificent. The other whispers that some truths are still out there, waiting behind layers of dust, distance, and doubt. Together, they form a spectrum between clarity and confusion, between data and desire, between what stars are and what we dream they could be. They are not just two giants. They are opposing poles in the vast theater of stellar evolution. One dimmer, closer, known, the other brighter, farther, uncertain. They are not fighting for the throne. They are defining its shape, and perhaps that's the lesson. There will always be stars larger than our models allow, brighter than we can explain, stranger than we can classify. Some we will measure, others we will imagine, but when they appear side by side, they reveal not just the scale of the cosmos, but the scale of our own unknowing. And in that contrast, between precision and poetry, we find something more lasting than either: perspective. To study dying stars is to study what it means to live at all. Why are we so obsessed with the largest stars? Why do we chart them, name them, compete over which one is bigger, brighter, stranger? Is it science, curiosity, wonder, or is it something deeper, something closer to the soul? Because to gaze at UY Scuti or Stephenson 218 is not just to observe cosmic phenomena, it is to feel something ancient and intimate move within us. They are dying, and so are we. They are expanding, and so are we. They are ungraspably vast, but they are disappearing, and so eventually will we. We don't just want to know the stars, we want to see ourselves in them. We search the universe for reflections of our own condition, our fragility, our power, or longing for permanence. UY Scuti pulses, shedding pieces of itself. Stephenson 218 leaks light and mass into the dark. They are magnificent, but broken, brilliant, but unstable. Just like us, we imagine we are solid, bounded, whole, but like stars, we are made of contradictions. We are matter and memory, fire and fear, driven by pressure and held in place by gravity, held together by forces we barely understand. We live with the illusion of permanence, but we too are bleeding into the void, second by second, moment by moment. And perhaps that's why we feel awe when we look at red supergiants, because deep down we recognize the pattern, the slow, beautiful collapse of something that once burned so bright. UY Scuti and Stephenson 218 are not just stars. They are archetypes. They are metaphors for aging, letting go, the paradox of expanding even as you near the end. They teach us that bigness is not the same as strength, that even the largest things in the universe are not immortal. They teach us that truth changes, that today's largest star may not be tomorrow's, that facts evolve, that myths shatter. They teach us that beauty often hides in decay, and that dignity does not require certainty. Consider this. UY Scuti was once thought to be the biggest. Then it wasn't. Stephenson 218 may be the biggest, or it may not be anything close. And yet, we still care. Why? Because size is not the point. The point is the story, the unfolding, the becoming. We live in a culture obsessed with records. The tallest building, the fastest runner, the richest person, the biggest star. But these are temporary crowns. They rise and fall with the data. What remains, what matters, is the awe they invoke, not because they are the biggest, but because they show us what's possible and what's fragile. There's something else too. Stars like UY Scuti and Stephenson 218 are incomprehensibly far away, thousands of light years. We will never visit them, never orbit them, never touch their dust. And yet, their deaths will shape our future. Their outflows will seed the galaxy with heavy elements. Their explosions will compress gas clouds into new stars. Their remnants will echo through time. In a sense, we are their descendants, and in another, they are our ancestors. Because everything we are, our blood, our bones, our breath, was forged in stars like these. So perhaps when we compare them, study them, question them, we are not trying to understand the cosmos. We are trying to understand how we fit into it. We are trying to answer questions too large for numbers. What is the purpose of greatness? Can something be magnificent and still vanish? What remains after the light goes out? UY Scuti's rhythmic pulses, Stephenson 218's slow disintegration. These are not just stellar processes. They are cosmic sermons. They remind us that even giants must yield, that even light must one day flicker, that even the most radiant lives are defined by how they end. But here's the gift. Neither star dies alone. Their particles scatter, their elements merge, their stories echo in our language, our art, our imagination. Their deaths will give birth to new worlds. And isn't that what we hope for ourselves? To become more than our body, to become legacy, to become matter transformed, not remembered for our size, but for what we left behind. So what do the giants teach us? That the universe is not built on permanence, but on transformation. That light is not eternal, but cyclical. That endings are not erasure, but re-entry into a larger story. And that our lives, like theirs, matter not because they are infinite, but because they are brief, brilliant, and shared. What if the largest star is not one we can measure, but one we can imagine? There is no tallest mountain in the universe, no final flame, no ultimate boundary, only thresholds that whisper, go further. We speak of stars like UY Scuti and Stephenson 218 as the largest, but that word, largest, is a trick of perception, a product of where we are, what we can see, and how brave we are in letting go of the known. Because in truth, there is no such thing as the biggest star. There is only a question. How large can reality allow itself to become before it stops being what we expect? When we crown a star like Stephenson 218 as the record holder, we are not declaring a fact. We are telling a story about edges, about longing, about our deep human need to find the outermost rung of the cosmic ladder and say, this is it, this is the top. But infinity has no ceiling, and the universe, in its silence, in its sheer unbothered vastness, gently tells us that, over and over. There may be stars beyond Stephenson 218, larger, cooler, more invisible, drowned in dust in some forgotten arm of a distant galaxy. Or maybe here, in our own Milky Way, their light still making its way toward us. A journey that began before we ever existed. Perhaps they died long ago, and we're only now beginning to hear their final breath. Or maybe they haven't even formed yet. Maybe the largest star the universe will ever know hasn't been born, because the story is still being written. And that's the cosmic joke. We are obsessed with finding the biggest, as if the universe has finished growing. But it hasn't. It's still becoming. Infinity is not a number. It's a direction. It's a spiral, a pulse, a breath that never ends. And when we reach what we think is the edge, the farthest galaxy, the oldest star, the biggest supergiant, we don't find a wall. We find a mirror, a reflection of our own need for boundaries, our own discomfort with mystery, our own fear that if we don't label the extreme, we'll somehow be lost in the middle. But there is no middle, no edge, only movement, only expansion. UY Scuti was once the largest, then it wasn't. Stephenson 218 may be the current title holder, or not. But what if the point was never the measurement? What if the point was the invitation to imagine something larger, to ask better questions, to embrace the uncertainty not as failure, but as freedom? Because the moment we say, this is the biggest, the universe leans in and whispers, not even close. We want numbers, but the cosmos offers metaphors. We want rankings, but the stars offer silhouettes of impermanence. We want winners, but the night sky is not a competition. It is a canvas of unfolding truths, and in that unfolding, we find something greater than any radius, any luminosity, any spectral type. We find perspective. When you look at a star like Stephenson 218, whether it's truly the biggest or not, you are staring at a question so massive, it bends your sense of self. And that bending, that humbling, that dissolving of ego in the face of something ungraspable, that is the point, not the measurement, not the certainty, but the awe, the sense that you are part of something too large to name and too beautiful to ignore. Because here's the final paradox. We measure stars in solar radii, luminosities, parallax shifts. We chase precision. But the part that moves us, that lives inside us long after the numbers fade, is the unmeasurable, the feeling, the breath caught in your throat, the quiet voice in your chest that says, "This means something." And what it means is this, that you, on this tiny blue dot, with eyes and questions and bones made from stars, are capable of imagining things larger than you can comprehend. And in doing so, you are not small, you are cosmic. So yes, measure the stars, chart their courses, revise the records, update the databases, but never forget, the greatest discoveries are not the stars we find. They are the stars we become when we let go of limits and look up with wonder.